So today I'm going to explain you Euler's formula, and I'm going to give a really cool argument using spherical geometry. Okay, so what's Euler's formula about? Well, you take any convex polyhedron, right? For example, that could be the cube over here, right? Or it could be the tetrahedron, or a cube with a rooftop, or something that I can't even draw, like icosahedra, dodecahedra, anything complicated that you can think of. Just make sure it's a convex polyhedra and count up the number of vertices, edges, and faces. So in case of the cube, 8 vertices, 12 edges, 6 faces, 4 vertices, 6 edges, 4 faces in case of the tetrahedra. In case of this object, you can count them all up as well. And take this algebraic expression. So vertices minus edges plus faces, whatever object, that polyhedra you take, this number is always equal to 2. And I guess Euler was the first person to recognize this. And he also gave an argument for it. Now, the argument we will give for this really cool fact will use spherical geometry. So since I'm not assuming that you know anything about spherical geometry, so let us learn in the next few minutes the basics of the geometry of the unit sphere. So I'll only be working on the unit sphere because that's enough for me to prove Euler's formula. But if you want to work on any radius sphere, the formulas are the same. It's just that you have to rescale by the length of your radius. All right, so let us take a unit sphere and let us take 2 points on it, right? So in this case, a point B and a point A. And really the question is, if I can only travel along the sphere, what are shortest length segments, right? So what are spherical segments? What is the curve that covers the smallest amount of distance between 2 points? And then you quickly realize that the shortest length curve is nothing but the great circle that collects the 2 points A and B. So how do you construct a great circle on a sphere? Right, so you take the 2 points that you want to collect, in this case A and B, and throw in also the center of the sphere, O, right? So 3 points form a plane, and then the intersection of the plane and the sphere is a great circle, right? And then you take the arc on this great circle that joins A and B, so that will give you the spherical segment AB, or you can call it the spherical arc. Okay, so that's how you construct segments on the unit sphere, right? By taking great circles. Now, the other thing that you want to understand is how are angles understood in a surface, on a sphere. So what's a spherical angle, right? So I take 3 points, A, B, and C on my sphere, and the question is, how do I measure the spherical angle ABC? Well, it's real simple, right? So here, you already know that in order to understand the arcs AB and BC, right, you need to take planes that contain these points and the origin, right? So this plane here cuts out the arc AB, and this plane here cuts out the arc BC, right? Now, if I want to understand the spherical angle ABC, that's nothing but the angle between these 2 planes that I just constructed, right? So spherical angles are really angles between the planes that cut out the great circles in question. Okay, good. So we understand what spherical segments are, and we understand what spherical angles are. So now let's discuss areas. So the most basic area, the most basic object on a sphere, on the surface of a sphere, is a spherical sector, right? So the spherical sector is the area that's cut out between 2 great circles, right? So you take great circles, and they're always going to intersect each other, and they're always going to determine a spherical sector, right? So the question is, what is the surface area of this spherical sector? So what you immediately realize is that whatever the area is, right, of this blue shape that I indicated here, right? It's going to be proportional to the angle of the spherical sector. So in this case, it's alpha, right? So now think about this. If this spherical sector would contain the whole sphere, then this angle would be exactly equal to 2 pi, right? So if alpha is equal to 2 pi, then the spherical sector is the whole sphere. But what's the surface area of the unit sphere? Well, it's equal to 4 pi, right? So if the 2 pi angle gives you a 4 pi surface area, if the surface area is proportional to the angle, then the area of a spherical sector of angle alpha has to be 2 times alpha, right? And also, as I said, right, so if alpha is equal to 2 pi, then you recover the full surface area of the unit sphere. Okay, so now you know what the spherical sector is and how you compute its area. Okay, so now let me teach you something really cool about spherical geometry that's totally different from plane geometry. Okay, so take 3 points, in this case A, B, and C on a sphere and form a spherical triangle, right? So that means find the great circles along all these 3 points and then join them to form a spherical triangle. So there's the most basic question that you can ask is something that you do also in plane geometry. What is the sum of the angles in spherical angles in this triangle, right? So in this case, we have alpha, beta, and gamma, the 3 spherical angles. So you ask yourself, what is the sum of these angles? Well, in plane geometry, the answer is always pi, right? So in spherical geometry, however, and this is the first difference perhaps between plane and spherical geometry, it's pi plus the area of the triangle, right? So there's this area that the triangle covers, and then the sum of the 3 angles is equal to pi plus the area. So I'm going to prove you this really cool fact, and all you need to understand, all that goes into the proof is what we just understood. So the area of spherical sectors. Okay, so how do you show this nice formula here? Well, what you need to do is what's already on the diagram, right? So extend the sides of this spherical triangle as much as you can, right? So in other words, draw up the great circles that give you the sides, right? So if you do this, then what you will see is that on the other side of the sphere, you will see this triangle, A prime, B prime, C prime, that is congruent to the original ABC triangle. Okay, so why am I telling you this? Well, because what you get is a partition of the sphere that is going to be extremely useful for us, right? So what is the total area of the unit sphere? Well, it's 4 pi, right? So since the radius is 1, then the total area is 4 pi. Okay, so now these 3 great circles have partitioned the sphere in a really cool and useful way, right? So there are 2 triangles here that are congruent to each other, right? So A, B, C, and A prime, B prime, and C prime, right? So if I want to partition the area, I count twice the area of ABC, right? So that accounts for the triangle here in the front and the triangle in the back. Now, in addition, and it takes a minute for you to see this, but it's not too difficult, the total area that is left comprises of the area of 3 spherical sectors, right? So the first spherical sector is the sector you get from this outside angle to alpha, right? So it starts over here, and when you peel it off, you get this spherical sector here, right? So the next one, I won't draw it in because it will be difficult to see, given everything that's already up here. So the next part that we haven't accounted for starts with this corner, right? So this angle pi minus gamma, when you peel off this sector, right, you will see that you only have one more sector left, and that is the one that starts with, it starts from this corner up here, right? And it has angle pi minus beta. So these are all spherical sectors, and their areas account for 2 pi minus alpha, 2 pi minus beta, and 2 pi minus gamma, right? So all in all, we get that 4 pi, the total area of the sphere, is equal to twice the area of our triangle ABC. So let me erase everything here. So we go back to the beginning, right? So twice the area of ABC plus one of the areas of the spherical sector, the other area of spherical sector, and the third one, right? So if you add everything up, you get, do a bit of algebra, right? So from here to here, you get 2 alpha plus 2 beta plus 2 gamma is equal to 2 pi plus twice the area of ABC. You divide by 2, and then you get the formula that I have over here, right? So the sum of the angles in a spherical triangle is pi plus the area of the triangle itself. Okay, so something that will be really useful for us in the proof of Euler's theorem is also looking at the outside angles, right? So what are the outside angles in a spherical triangle? It's the same as in the plane, right? So in case of this triangle ABC, the outside angles are this one, and this one over here, right? So an angle plus its outside angle always add up to pi. So if you want to get the sum of the outside angles, so in this case alpha hat, beta hat, and gamma hat, if you sum them all up, it has to give you 2 pi minus the area of the ABC. You get this really quickly from this formula over here on the top. Okay, so you can go really quickly from triangles to polygons, right? So what are spherical polygons? Well, you take up endpoints on the sphere and you join them by spherical segments. And you might ask yourself again, what is the sum of all the interior angles, or all the angles? Well, it will be the same as in plane geometry, n minus 2 times pi. But again, you have to add in the excess area. So area of the full spherical polygon. Right? And again, how do you prove this? You prove this the way you prove that in case of the plane, right? The sum of the angles is n minus 2 times pi. You partition the polygon into, in this case, spherical triangles. And then you know the formula for each spherical triangle. You add up all the formulas in case of each triangle, and then it will give you this formula here. So I'll leave the details to you. It's quite simple. And again, you also get a formula for the sum of outside angles. So I will write that here in this form. So you can express the area of the spherical polygon as 2 pi minus the sum of all the outside angles. Okay, good. So now that you understand this, you will be surprised to know that we are ready to prove Euler's theorem, right? So let delta be our polyhedron, as complicated as they get. And then number of vertices minus number of edges plus number of faces should be equal to 2. Okay, so how does this have anything to do with spherical geometry? Well, let me show it to you. So you take your spherical polyhedron and put it inside your sphere, right? So maybe you have to zoom it down a little bit and put it inside the sphere. And once it's inside the sphere, project it onto the surface of the sphere. So this sounds quite complicated, but I guarantee you that you've seen this before. As a matter of fact, right, so this is how the icosahedron becomes the soccer ball, right? So place the icosahedron inside a sphere and project it onto the sphere, and then you get the soccer ball. Okay, so we will be working with the soccer ball, right? So what the really important thing here is that once you do this, the polyhedron will cover the whole surface area of the unit sphere. And then you get a bunch of extra geometry that you wouldn't see unless you project it onto the sphere. So what do I mean? So let P1, P2, and PF, all the way to PF, the spherical polygons that are the faces of our spherical polyhedron, right? So in case of the soccer ball, right, so P1 to PF will be a bunch of spherical hexagons and spherical pentagons. Right. So the total area of the unit sphere is equal to 4 pi, right? I can express that using the partition. In case of the icosahedron, right, it will be the partition that the soccer ball does to the sphere, right? So it will be the area of this bunch of, in case of the picture, right, so I have a bunch of areas of hexagons and a bunch of areas of pentagons, right? So I do that over here. Okay, so now I use the formula that I just learned in terms of outside angle, right? So each polygon, the area you can write up, so let me just roll back real quick. The area of that polygon you can write up as 2 pi's minus the sum of outside angles for that polygon, right? So in case of this spherical polyhedra, we sum up all the areas of the polygon, so that will be equal to 2 pi times the number of faces minus the sum of all possible outside angles that can appear, right? So this outside angle, sorry, that's not an outside angle. So this outside angle, this outside angle, this outside, all possible outside angles that you can write down. Yeah, those are not outside angles either, right? So things like this, right? So in case of this pentagon over here, right? So maybe I can write down all the outside angles for just for this pentagon, right? So this is just one pentagon here. Do it for all the hexagons, pentagons, and then all those measurements for all those angles will go in this sum here. Okay, good. Okay, so let's look at this sum here a little bit differently. Okay, so what happens if I sum up all the angles of my polyhedron at each vertex V, right? So if I just focus on a vertex V and I sum up all the angles, not the outside angles, the angles, right? So this will sum up to always to 2 pi. Okay. Okay, so let me denote by EV the number of edges meeting at a specific vertex V, right? So if I call this V, let EV the number of edges meeting at V, right? So in this case, it's 1, 2, 3. Okay, so since the sum of the angles meeting at each vertex is 2 pi, you know, a very basic algebra operation tells you that the sum of the outside angles at V is equal to what? Well, it's equal to pi EV minus 2 pi. Okay, good. So now what do? Well, I sum up these sums along all the vertices that I have, right? So you have all the outside angles at V, and now you're summing up across V, V being a vertex in your polyhedron, right? So that what will that give you? Well, it will give you all possible outside angles. Okay, good. And on the right-hand side, what do you get? Well, you get these expressions summed up across all vertices. Okay, so what's going on? So EV is the number of edges meeting at a fixed vertex V. Okay, but every edge has 2 ends, right? So that means in this accounting, every edge will show up twice. So this part of the sum will be twice the number of edges, and there's already a pi here, so I get 2 pi E. Okay, so when I sum 2 pi across all vertices, I get what? Negative 2 pi V. Well, we're almost done, right? So I look at the left-hand side. So this is the sum of all outside angles. What's that? Let me go back a little, right? So according to this formula here, that I'm underlining again, the sum of all outside angles is going to be what? 2 pi F, minus 4 pi. Okay, so I have that this here is equal to that. Okay, so let me divide by 2 pi. So then I get what? F minus 2 is equal to E minus V. You immediately see it, right? So you get V minus E plus F is equal to 2. Euler's formula. And I gave you a proof using spherical geometry. Okay, I hope you enjoyed this. Thank you very much for your attention.